In this video, we'll be using Boole's inequality, which we just proved, and applying that to random graphs and then analyzing them using that inequality. So first off, we need to define what a random graph is, and it depends on the model that we're using, but we're going to use the model by Erdo? I forget how to pronounce his name. Erdo, super famous mathematician, and Renyu, I'm assuming also famous. I have no idea. But I know he's super famous. Look him up. He's like everywhere in math. It's pretty impressive. Either case, we're going to let G and P be a random graph generator, and suppose G and P only creates simple graphs. So we have two parameters in this random graph generator. We have N, the number of nodes in the graph, and P, the probability that for every pair of nodes, that's the occurrence of an edge being formed between those two nodes. I think in our section of graph theory we said vertices, but they're also called nodes. So just be used to that notation as well. So for example, right, you have, let's say n equals 3 and p equals 1/2. Who knows how it's going to be formed, but you could have the graph that looks like that, right? And if p is almost 0, then it's likely that you're going to have no edges. Or maybe you'll have one, but it's likely that you'll have some sort of isolation. Okay. And of course, you can just imagine that you generate a graph randomly by connecting their edges of the nodes with some probability p. All right. So what we're interested in this situation is we want to calculate the probability at least one isolated node in the graph. Okay. So an isolated node is what you could imagine. It's a node that's not connected to any other nodes in the graph. So if we had a graph like this, this here would be an isolated node. Okay. And so we're wondering that if we generate graphs using this random graph generator, what's the probability that there's at least one isolated node in the graph? All right, so how we're going to do that, we're going to say let AI be event the ith node is isolated. Then the probability of at least one isolated node in the graph, that's the probability of A1 union A2 union AN. All right, that's the probability of at least one isolated node in the graph. And by Boole's inequality, we know that that is less than or equal to the sum of I equals 1 through n, probability AI. All right, so our goal may be not to be calculating exactly what this probability is, but at least give a upper bound on it. Okay, so an upper bound meaning that it's less than or equal to or at most. Let's calculate probability A1. That is the probability that node 1 is isolated. Okay, and you can think of it like this. Node 1, let's say this is node 1, and then you create a bunch of other nodes in the graph. And you're going to go to each one of these and you're going to say, okay, am I connected? Do I have an edge connecting myself with 2? And remember that edge is formed with P, and it's not formed with 1 minus P. So 1 going to 2, so you can either say yes or no. Yes edge or no edge with node 2. And remember, you form a edge with probability P, which means you form no edge with 1 minus P. All right. And then once you're done with that, you're going to go look at, let's say, 1 with 3 now, and you're going to do the same, and they're independent of each other. So now we go again. Node 3, and again you say yes, 1 with node 3, or not with 3, and so forth. Remember, this is formed with probability P, and no edge is 1 minus P. So no edge and no edge would mean you're isolated so far. So probably the node 1 is isolated as 1 minus P times 1 minus P. That would be if n equals 3. But in general, we're going to have to look at all these other ones that you could not form an edge with. And in general, if 1 is looking at everyone else, there's n minus 1 of these nodes that you're going to have to do. So I'll write that out. So node 1. If it does not, I should say. If it does not form an edge with the other n minus 1 nodes. Okay, and so therefore probability A1 equals 1 minus P to the n minus 1, and that's by the multiplication rule. And these are independent events. Right, independent trials, I guess you could say. You're just looking, this node 1 right here is looking at each other node and saying, okay, yes or no, yes or no, yes or no. And it's saying no with probability 1 minus P, independent of all the other ones. In a similar argument, you could say probably A2 is the same. And in fact, for any of these AIs, you have 1 minus P to the n minus 1 is the probability that they are isolated. And that follows by symmetry. Which is a more advanced topic in probability, but you could argue the same. It's not dependent on whatever happened with A1. We're not asking about the intersection of those events. We're just asking on its own, what's the probability of it having an isolation? All right. And so we come back up here and we get to say, all right, these are all the same. They're all 1 minus P to the n minus 1, and there's n of them. So therefore, A1 union A2 union AN, which is less than or equal to the sum of those events, and that's equal to n times 1 minus P to the n minus 1. Because there's n of these AIs in the sum, and each one is 1 minus P to the n minus 1. Which is a pretty neat result, and it has a interesting consequence. In other words, this is saying probability of at least one isolated node is less than or equal to n times 1 minus p to the n minus 1. So in a random graph where we're generating n nodes and we're connecting every pair with a probability p, you have the probability of at least one isolated node is less than, is at most, n times 1 minus p to the n minus 1. And what's interesting, I think, is if I take this limit, that's less than or equal to the limit infinity n times 1 minus p to the n minus 1. So I am glossing over some technical details of limits and probabilities. Let's not get hung up on that. Let's just kind of take our intuition here and know that it does follow. Okay. So we got limit of n infinity, and then we have two competing terms here, and hopefully you've taken at least pre-calculus to know that this here, well, 1 minus p is, that's between 0 and 1. So it's a small number here. And then we're taking that small number and we're raising it to the n minus 1, which is going off towards infinity. And hopefully you know that a really small number taken to an exponent of a huge number, infinity, is going to decrease exponentially. So that blue piece here, that's exponential decay, and that's going to 0. On the other hand, we do have this n here, and that's going off to infinity. But this here is what we call linear growth. And hopefully you know that exponential decay is much stronger than linear growth, and it's always going to win. So what does that mean? That leads us with the interesting result that does limit n goes to infinity, probability at least one isolated node is converging to 0. What does that imply? That implies that as we let this random graph create a whole lot of nodes, the probability of no isolated nodes goes to 1, which is intuitive and counterintuitive at the same time. It's saying, like, as you increase the number of nodes to be super big, like 1 billion nodes, you would think that, and you're just randomly connecting them, you'd think that there would be at least one, but it turns out that there isn't at least one, that the probability of having no isolated nodes, or that everything is somehow connected by at least one thread, is converging to probability 1, which is a pretty cool result. All right, so I'm not going to expect you to reproduce this analysis on your own, but I will expect that you at least can remember this result. And then I'd probably have you just plug in some values for n, 1 minus p, and so forth to get it like a numerical for like n equals, I don't know, 6 or 10, and p equals 0.3, and just get an upper bound on it. Because it's an upper bound, this may be greater than 1 sometimes, depending on the values. But know that for n big enough, then this eventually will make it small to be less than 1, and actually it goes towards 0. All right, hopefully you like that analysis of those random graphs and using probability. So induction, probability, and graph theory all in one lesson. Hope you enjoyed it. I'll see you in the next video.